Welcome to a presentation brought to you by the American Wood Council. Thank you for your participation in our webinar today. This webinar is intended to provide general information only and does not constitute professional or engineering advice. Please note that this webinar is being recorded, and by remaining a participant, you automatically consent to such recordings. If you do not consent to being recorded, please disconnect from the session. This presentation is worth 1 LU HSW with the AIA and 0.1 credits with the ICC. To receive credit for the course, you must attend this webinar for a minimum of 50 minutes. At the end of 50 minutes, you will see your certificate appear on your webinar console. Your certificate will also be uploaded into your learner profile on learn.awc.org, provided you registered for today's webinar with the same email address as your account profile. At the end of today's session, our presenter will have a live Q&A with the audience. Please input your questions into the Q&A panel throughout the session. And now, for today's presentation.
Good afternoon. My name is Matt Hunter, and I'm the Northeast Regional Manager for the American Wood Council. Today, we are going to present our most recent course, An Introduction to Mass Timber Buildings in the IBC, or the International Building Code. Any education materials desired to be copied or distributed by anyone other than AWC staff must have copyright approval from AWC. So what are we going to talk about today? We will identify the differences between the traditional heavy timber construction type and the new mass timber construction types, and we will provide a brief overview of some of the engineered wood products routinely associated with mass timber structures. Next, we will examine the consensus-based work that the ICC's Tall Wood Building Ad Hoc Committee did in reviewing the tall mass timber code changes that were adopted into the 2021 IBC, as well as analyzing some fire tests that were performed in support of these changes. Then we will introduce the permitted overall maximum height and number of stories permitted under the new Type 4A, 4B, and 4C construction types. And lastly, we will examine the non-combustible protection as it applies to mass timber and the importance it has when determining adequate fire resistance under the IBC. We will introduce mass timber buildings that fall under the Type 4A, 4B, and 4C construction types. Next, we'll provide some background and history on how the tall mass timber provisions were reviewed and promulgated into code changes prepared by the ICC's Tall Wood Building Ad Hoc Committee. Then we'll discuss some of the heights, number of stories, and areas associated with mass timber structures. And finally, we will review the importance of non-combustible protection and its contribution to the overall fire resistance ratings required with the 3 mass timber construction types, and review when exposed wood areas are permitted specifically under the criteria in Type 4B construction. Let's begin by giving an overview of the various forms of mass timber and a brief history of some of the more recently developed ones. So when we talk about mass timber, what does that actually mean? What do these buildings look like? How is it different from a post and beam or traditional heavy timber building? This slide is depicting the newer mass timber style of construction. In the center, we have a hybrid steel, glulam beam, and cross-laminated timber building on the campus of Penn State University. And the photo on the left is the Samuel Brighouse Elementary School in British Columbia, Canada. Notice the undulating form of the glulam beam above the curtain wall assembly. And on the far right is the University of Idaho Central Credit Union Arena for both men and women's Vandals basketball, located in Moscow, Idaho. Before we move on to the next portion of this presentation, I wanted to briefly note one very important point. As I hope you've gathered from the pictures we've seen so far, mass timber construction is very different from conventional, repetitive light frame construction. In mass timber construction, the members have significantly larger cross-sectional dimensions and are much further apart. Also, there tends to be fewer concealed spaces, and these spaces are required to be protected if they are combustible. Consequently, the structural designs and response to fire of a mass timber building are significantly different from how a repetitive light frame structure would be affected. These inherent differences provide the basis of historical prescriptive provisions for Type 4 HT construction, as well as for the new mass timber construction types 4A, 4B, and 4C. The concept of mass timber, or tall wood buildings, is not a new one. Many of these older buildings, including the examples shown here, have still not reached the end of their service life. These historical timber buildings were constructed using solid sawn heavy timber beams and columns. Exterior walls of these buildings are non-combustible and typically associated with masonry construction. And with a few exceptions, they were typically built in a manner that did not result in concealed spaces within floors and walls. This type of construction is now prescriptively addressed in the IBC as Type 4-HT. The photo on the left is the historic Butler Building in Minneapolis, St. Paul, and it is a 9-story post and beam heavy timber building. On the right, we have an in-progress photo of the iconic Brock Commons building, which at the time was the tallest mass timber building in North America and is currently in use as student housing on the campus of the University of British Columbia in Canada. It has a concrete podium with reinforced concrete stairway and elevator hoistway shafts and 17 stories of glulam and CLT floor ceiling panels. We'll take a look at the video that documents its construction on the next slide. So this is the 18-story Brock Commons building in British Columbia. Again, as we mentioned previously, it's student housing. So it has a reinforced concrete podium on the base floor. You can see the two structures there that are reinforced concrete are stairway shafts and also elevator hoistway shafts. They use these to provide seismic performance and lateral resistance for this particular project. You can see the description and the sizes of the glulam columns that support the cross-limited timber floor and ceiling assembly, and some data as the slideshow progresses about how much time it takes to install each individual column, and the crews installing the panels on top of the columns. The construction speed here is annotated here on the slide, about 2 floors per week. There's no waiting for concrete to cure or reach structural strength. Time period 7, 14, 20 days, et cetera, for concrete. And it goes together pretty quickly. A very, very small crew is typically required for these projects. You see the crane operator there is picking them right off of the trucks. It's very typically quiet associated with these jobs, not as much noise as conventional construction. And everything, all the panels are CNC machined from the assembly plant, from the manufacturing plant. So there's very, very little waste. And you can see the speed of construction there. Approximately 2,233 cubic meters of wood were used. And these have significant positive impacts about sequestering carbon and carbon dioxide benefits. So just a really, really innovative and interesting project. And this is no longer the tallest structure in North America. There's some other projects that we'll take a look at during the presentation. So mass timber is a term that is used to describe wood products and built-up assemblies having large dimensions and substantial mass. This is a list of those elements often associated with mass timber, if they are large enough to be in compliance with the minimum size requirements for heavy timber as specified in Table 2304.11 of the 2021 and 2024 editions of the IBC. Mass timber is a separate building system, was really born because of one new product, cross-limited timber, or CLT. CLT represents a paradigm shift in wood construction because of the new structural and fire resistance characteristics it represents. Never before have we contemplated solid wood floor and wall sections used in a similar manner as concrete walls and floors. CLT is typically dimension lumber, 2x lumber, laminated in a crosswise fashion, layer upon layer, to make solid wood floor, wall, and roof panels up to 20 inches thick and 60 feet long. What has been used so far is typically more like you see here, panels between 6 and 9 inches thick. CLT panels are typically fabricated in odd number of laminations, 3, 5, 7, 9 plies, etc. This slide provides a brief summary of the history of CLT. The first patent for CLT was obtained in France in 1985. The first constructed projects occurred in Switzerland and Germany in 1993. In 1995, press technology developed, making manufacturing easier and more precise. Multi-story applications came in 1998 with a residential building in Styria, Austria. Between 2000 and 2010, European builders expanded their use of CLT and mass timber significantly. For example, due to regulatory programs promoting green and sustainable construction, England has seen a tremendous increase in the use of mass timber construction, with over 500 buildings built to date. The U.S. Building Code, known as the International Building Code, or IBC, adopted provisions and definition recognizing CLT as a heavy timber product starting in 2015. Another type of mass timber which has been in use for several decades is glue laminated timber, also known as GLT or glue-lam. Glue laminated timber beams meeting the minimum dimensions can be used in heavy timber or type 4 HT construction and the mass timber construction types as well. Standard widths of glue-lam members can exceed 12 inches and standard depths can be up to 60 inches or 5 feet. Glue-lam members are constructed with smaller dimensional lumber, typically nominal 2x lumber, which are adhered to each other using heat-resistant exterior grade structural adhesives. In glue-lam, all the laminations are oriented such that they are parallel to one another. Glue-laminated members are typically used for flexural applications, for example, beams and girders, or compression applications such as posts and columns. However, they may be used in tension applications too. Well, you can see some structural similarities with the student housing building project at Brock Commons. The Ascent project exceeded the prescriptive limits for tall mass timber in the 2021 IBC. The Ascent project has a 6-story concrete podium or pedestal, and then 19 stories of glue-lam columns with CLT floors and ceilings. Currently, the Ascent building is the tallest mass timber structure in the world. Now let's discuss the critical role the ICC's Tall Wood Building Ad Hoc, or TWBAH for short, had in reviewing the mountains of data required for the code change proposals associated with mass timber buildings. The TWBAH was a balanced committee that was intended to develop consensus by input from experts throughout the country, starting with experienced building and fire officials, leading structural and fire protection engineers, fire protection experts, including some leading fire protection engineers and consultants, and finally, representatives from all building material and construction-related industries. The meetings were open and participated in by any interested parties, including participation in work groups. Some of the key tenets from the TWBAH utilized when considering the tall mass timber code changes provisions were: no collapse under reasonable scenarios of complete burnout in the absence of or application of automatic sprinkler systems, no unusual levels of radiant energy exposure from the tall wood building to adjacent buildings, no unusual response to typical radiant energy from a fire next door to the mass timber or other exposure, no unusual fire department accessibility issues. There are often fire department accessibility issues on construction sites, so the committee felt it was important to introduce explicit provisions to ensure firefighter access. Egress systems must protect occupants during escape time, plus an additional factor of safety. And lastly, suppression systems must be highly reliable. In fact, there are redundant suppression systems required for any mass timber building over 120 feet in height. After evaluating these performance objectives, the TWBAH was satisfied that all performance objectives were successfully met. One of the various work groups established to review potential code changes was the fire work group. They were tasked with determining realistic fire tests to evaluate the fire resistance and performance of a building constructed with mass timber elements. The express purpose of the test series was to evaluate occupant egress tenability and firefighter attack tenability. The series, which consisted of 5 separate tests, was conducted at the ATF Fire Research Laboratory in Maryland and was supervised by U.S. Forest Products Laboratory staff. Here we have the information appropriate to each of the fire tests. Each new construction type in the 2021 IBC was based on at least one of these test scenarios. The fire test plan was drafted with the input of career fire service members who had real-world experience with fires in multi-story buildings and dictated the configuration of the buildings tested at the ATF lab. Through penetration protection and connection protection were also included within the test structure. It should be noted that the ATF test structure included not only CLT members, but also glue laminated columns and beams. You can see the attached corridor and two-story configuration of the test assembly. The fuel load was based on a North American study of fuel loading for residential use groups. In fact, to ensure rigorous test conditions, furnishings and additional fuel load were added to achieve a fuel load equivalent to the mean plus one standard deviation. The actual fuel load used within the test structure corresponded to approximately the 85th percentile of residential fuel loads based on the survey. Regarding the fuel loading, megajoules and megawatts might not resonate with some of our attendees in the audience today. For better comprehension or comparison, the energy release equivalent for test 2 and 3 would be like igniting 360 gallons of gasoline within the test compartment. No combustible material is permitted in concealed spaces of the soffits, which had gypsum protection on the mass timber, light gauge, cold form steel stud framing. Each unit had plumbing, mechanical, and electrical penetrations, but no utilities were connected. The penetrations were protected pursuant to current code provisions to determine their performance in mass timber structures. In test number 2, 30% of the ceiling areas in the living room and the bedroom were left exposed. This amounted to 20% of the overall ceiling area throughout the apartment, which is the maximum amount permitted under the 2021 IBC Type 4B construction type. The photos at the bottom of the slide show the exposed ceiling areas, exposed CLT areas prior to the test. So we're going to watch a highly compressed video of test 2. Remember that test 2 was the one with the exposed portion of mass timber on the ceiling. The test lasted for 4 hours, but this is a time-lapse video which compresses that down into about 3 minutes. It was produced by the folks at ATF, and I think they did a great job with it because it includes simultaneous views from multiple cameras placed throughout the structure. I'll start the video here. Here you can see the multiple camera angles. You can see the fire service in fully protected gear entering the compartment. They're going to be igniting a gasoline-soaked rag in the same location for all the tests, which would be in the lower base cabinet area in the kitchen. So the kitchen and the living room are combined, and the bathroom and the bedroom are combined as well. And there's a demising wall between those two spaces with gypsum wallboard and light gauge steel studs. So you can see our fire service are about to ignite the gasoline soaked rag. And I'll speed things up here in the interest of time. So it should be noted that just the contribution of the fuel from the base cabinets was enough to ignite the upper cabinets, and the combination heat release from the lower and upper cabinets is enough to cause flashover conditions in the great room compartment. So we're approaching flashover in the living room at approximately 12 to 13 minutes. You can see the flames rolling on the ceiling there. And this will ensure the temperatures in the compartment reach flashover, which is measured 1 foot from the ceiling and 600 degrees C. Speed this up a little bit. So now we have flames rolling out of the opening. The cell in the bottom right is an infrared camera showing the heat release from the compartments. Notice that not all the furnishings have spontaneously ignited. The 2 chairs there are just about to spontaneously ignite now, but everything is in flashover conditions and fire growth in the first compartment. You can see in the cell on the middle right of the video here that we have the mattresses wrapped up in plastic. They're foam mattresses. You can see all the combustible cribbing throughout the room, stacked in the room, and the heavy black smoke rolling through the open door. This door opening is going to allow enough heat and smoke into the joint bedroom and bathroom compartment to cause flashover conditions in the bedroom. You can see the mattresses the coverings are starting to pyrolyze there, and off gas, and they're going to spontaneously ignite with flashover. The image on the bottom left of the video is the actual fire-rated door at the end of the corridor. And the image next to that, you see a little flame front penetration through the compartment door, through the dwelling door into the hallway. So I'm going to speed this up. You can see the performance of the 20-minute rated door. Here, it'll fall into the opening, but you can clearly see that we're in the decay phase. The infrared imagery has drastically dropped in temperature, and they will continue to monitor this test to ensure that there's no fire regrowth conditions. And I'll speed it up to the end. Here are the still shots from test 2. Ignition to flashover in the living room is about 12.5 to 13 minutes. Flashover in the bedroom is approximately around 17 minutes. And then the fire proceeds to burn out and the mass timber elements self-extinguish. Notice the char formed on the exposed mass timber ceiling areas just as predicted. In this photo, you can not only see the post-fire condition of the CLT, but also that of the glulam columns and beams. Again, the areas protected with gypsum were uncharred, with the exception of minor localized surface charring in limited spots, such as at the lower edges of the glulam beam. The exposed area of the ceiling can be seen here as the charred rectangular area to the upper right of the man in the ladder. Just like for test 4, in test 5, all mass timber surfaces were fully exposed in both the bedroom and living room. The sprinklers were purposely prevented from activating normally, then were manually charged 23 minutes after the time at which the automatic sprinklers activated in test 4. This simulated a scenario in which the sprinklers failed to activate automatically, but are then manually charged at the fire department connection by the fire service upon their arrival at the scene. Flashover conditions were reached in the kitchen, and the bedroom was very near reaching flashover. Within 7 minutes of manually charging the sprinklers, the fire went from a fully developed stage to being effectively suppressed, as can be seen in the lower right photo. Some data on flashover time, performance of the compartment door, and sprinkler activation times are listed in this table. The full report was published by the U.S. Forest Products Lab in 2018 and is available on their website at the UL address shown here. All the fire tests were recorded on video, and these videos are available for free public viewing. Now let's review these new construction types. Specifically, they are types 4A, 4B, and 4C. I'll explain what each of these are and the prescriptive provisions associated with each. A new definition was created to define mass timber. It is based on the same minimum cross-sectional dimensions as traditional heavy timber. The minimum dimensions for heavy timber are located in table 2304.11. This slide is providing information on the minimum sizes necessary to be considered mass timber. Details are found in IBC sections 2304.11 and 602. Here is IBC table 601 showing the new columns for the 3 new types of construction. Notice that the fire resistance rating requirements for type 4A are exactly the same as those for type 1A. This is not a coincidence. Even though mass timber is combustible, it has to meet the same stringent fire resistance of the traditional non-combustible construction types. Likewise, both 4B and 4C have exactly the same fire resistant rating requirements as type 1B or 2 hours. The three new types of construction are described here. I mentioned earlier that these are designated as types 4A, 4B, and 4C. The TWB began by acknowledging that fully protected mass timber performed like type 1A construction. Thus, they chose to call that fully protected condition type 4A. A similar correlation was drawn to type 1B, so the partially protected condition was called type 4B. And simply to complete the list, fully unprotected mass timber was called type 4C. Traditional heavy timber was left unchanged in the code, except that the name or designation was changed to type 4-HT or type 4HT instead of simply type 4. Here's a summary and a visual depiction of what an 18-story type 4A building might look like. All the fire resistance ratings, non-combustible protection criteria, and other building requirements are shown in the table. And here we are depicting a 12-story type 4B building with the applicable fire resistant rated and building criteria listed in a similar table. Lastly, we are depicting a fully exposed type 4C mass timber building. But notice that even though it is permitted to have fully exposed wood surfaces, the criteria for 2 hours of fire resistance is exactly the same as the taller type 4B construction type. Again, the code has always addressed equivalent risk with equivalent performance. Even though the type 4C building is permitted to be fully exposed, it still meets the old type 4 heavy timber overall height limit of 85 feet. Okay, let's review the prescriptive limitations on building sizes. In other words, the heights and areas, which are associated with these three new construction types. Here are the new columns in Table 504.3, which specify the allowable overall heights in feet. Notice that the heights in feet are commensurate with the construction types with similar ratings, except type 4A does not get unlimited height. The unsprinklered limits are capped at those corresponding to the existing limits for type 4 HT. The TWB decided that type 4A should be somewhat taller than type 4B. However, the TWB, continuing to take the more conservative approach, did not find it acceptable to allow the unlimited heights of construction type 1A to be applied to type 4A. Instead, a multiplier of up to 1.5 times the height of type 4B construction was utilized. Here's an excerpt from the table which specifies allowable building heights in stories for the three new construction types. Notice that the unsprinklered height limitation for any occupancy is equivalent to the existing code height permitted for heavy timber. The code work group established a relationship between types 1B and 4B, and then between types 1A and 4A. Then the TWB examined each cell for efficacy and reason, and adjustments were made accordingly. Here's an excerpt from the allowable areas table. Since both types 1A and 1B are mostly unlimited areas, the TWB committee looked to existing type 4HT as a basis for area limits. The committee developed a relationship for each of the new types of construction. You can gain valuable insight into these and other code changes by reading the code commentary for each ICC publication. Again, the group looked at each occupancy type, risks, consequences, etc. Based on those assessments, professional judgment was applied to each cell, and the table is the result. It should be remembered that these are the per story allowable areas. In a multi-story building, the per story area in the SM or sprinklered multi-story value area can be multiplied by 3 to get an allowable building area. As you go higher than 3 stories, the average story will be reduced in order to limit the entire building area to 3 times the SM or sprinkler multi-story value allowable floor area. So your allowable floor areas will be reduced as the building gets higher. This is quite a contrast to the unlimited areas in Type 1. Also, keep in mind that there are no rating reductions for the new Type 4 construction types that are provided for Type 1 construction. And of course, for all 3 of these new construction types, sprinklers are required, and no combustibles are permitted on the outside of exterior walls or within concealed spaces. This slide illustrates the height permitted for occupancy group B or the business occupancy, which is the tallest. The heights are the same for group R, except that Type 4C is limited to 8 stories instead of 9 stories. Lastly, let's go into the concept of fire resistance when discussing mass timber construction. Non-combustible protection, as defined in the 2021 IBC, is a new term, specific to the protection of mass timber. We'll talk about this a little later in the presentation. First, let's go into a little detail about something here. The mass timber provisions bring with them something new. There's a nuance here to fire resistance that is unique and specifically developed for the protection of mass timber buildings in these new construction types. What is shown on the screen now is the actual code text. The required fire resistance rating of mass timber elements is determined in IBC Table 601, and for specific provisions for exterior walls, IBC Table 705.5. The portion of the fire resistance from the mass timber itself is determined in accordance with Section 703.2, which provides 3 methods. 703.2.1 allows testing to ASTM E119 or UL263. 703.2.2 allows the use of analytical methods such as NDS Chapter 16 or the FDS Chapter 3. And 703.2.3 allows the use of approved alternative methods. We've seen how a primary premise for types 4A and 4B construction and their associated building heights, which we'll see later, is that these buildings should be able to withstand until burnout a contents fire that is not controlled by sprinklers or addressed by firefighters. This is a very conservative approach. And this means that for type 4A and 4B for this to happen, the non-combustible protection plays a particularly important role in that it provides for a contents fire to burn out, and the contents and any exposed mass timber can self-extinguish if the fire is never addressed. IBC section 722.7.1 addresses the minimum required proportion of non-combustible fire resistance for the overall rating of the element. That is to provide 2/3 of the fire resistance rating by the non-combustible protection. Here the code is explicit about how the fire resistance is accomplished. Simply the addition of the calculated fire resistance of the mass timber element itself to the fire resistance rating of the non-combustible protection. The code is going to provide minimums and assign quantities that can be added. The fire resistance protection required to be provided by non-combustible protection is specified in the new table 722.7.1 parens 1, as shown at the top of the slide. The fire resistance protection recognized as being provided by various non-combustible protection types is specified in table 722.7.1 parens 2. Note that the number of 5/8 type X gypsum board layers that would be necessary to achieve the required non-combustible protection is the same as the number of hours of fire resistance rating required per tables 601 and 705.5. In buildings of type 4A, B, and C construction with an occupied floor located more than 75 feet above the lowest level of fire department access, up to and including 12 stories or 180 feet above grade plane, interior exits are permitted to be constructed of mass timber elements. For interior exit enclosures in type 4A, height restricted, and 4B and 4C construction, the fire resistance rating of a protected mass timber element can be determined by adding the FRR of the unprotected wood member to the non-combustible protection FRR applied to exposed wood. However, the FRR must be met on both the shaft side and the room side of the mass timber elements per IBC section 602.4.1.6, 602.4.2.6, and 602.4.3.6. One thing that is different in the 2024 IBC is in item 1 for type 4B construction. Specifically, the limit on exposed mass timber on the ceiling will be increased from 20% of the floor area to 100% of the floor area. This was justified based on extensive large-scale fire testing that was performed at the Research Institute of Sweden in 2020, which, among other things, validated the performance of heat-resistant adhesives in preventing char fall-off and preventing fire regrowth conditions, provided that the walls were covered with non-combustible protection. Again, typically, the fuel load in the compartment is exhausted as the room and contents are completely consumed in the fire. Once the heat release rate decreases from loss of fuel, the exposed CLT surfaces self-extinguish. Thus, they no longer contribute to the fuel load and heat release rate associated with the fire. Here you can see the provisions for unprotected portions of mass timber walls in type 4B construction. In exception number 2, you can see that the columns and beams that are not within the walls or ceilings are permitted to be unprotected with regards to calculating the floor or dwelling unit area values. In other words, their area does not affect the calculations of other areas to be exposed under this section. Some of the key fire performance features that have been built into the new provisions for type 4A through 4C construction are listed here on this slide. For example, the new IBC provisions require that mass timber elements be protected with non-combustible protection as specified in section 602.4. Structural elements are required to have a fire resistance rating as shown in IBC table 601 and 705.5. The adhesives used in CLT are required to be qualified through a series of both small-scale and large-scale fire tests that are required for glulam and structural composite lumber wood products to ensure that they do not undergo heat delamination, which could lead to fire regrowth, and combustible light frame members are not permitted. You may have seen in some of the pictures I showed of the ATF test structures that cold-formed light gauge steel studs were used for the non-load-bearing interior partitions and infill. In fact, no combustibles are allowed in any concealed space except for those materials which are currently allowed in plenums by the International Mechanical Code, for example, such as insulated wires. Also, in type 4A and 4B, floors are required to have non-combustible topping that is at least 1 inch thick. Typical examples of this would include cast-in-place concrete or flowable gypcrete type products. In all 3 of the new construction types, everything outboard of the mass timber and exterior walls is required to be non-combustible, except provisions for water-resistant barriers, which must meet specific fire performance criteria. Also, All exterior mass timber walls in all three of the new construction types are required to have one layer of 5/8 type X gypsum on the outside. Depending on the fire separation distance, additional non-combustible protection is required where an exterior fire resistance rating of greater than 1 hour is stipulated by Table 705.5. And of course, it is not explicitly called out here, but the interior side of the exterior walls are also required to meet fire resistance ratings as stipulated by Table 601. As for the interior side of the exterior walls, you always have to design the required amount of fire resistance to resist the spread of heat, smoke, and flame from one place of origin to another of the building for a prescribed time. In the case of Type 4A, there would be no exposed mass timber elements, and it would require 3 hours of fire resistance, accomplished by the 3 layers of 5/8 Type X gypsum and the contribution from the structural mass of the mass timber elements themselves. This section demonstrates the required protection limits and applications for Type 4B construction. This interior application rating is for a fire resistance rating of 2 hours, and thus the non-combustible protection is 2 layers of 5/8 Type X gypsum, not 3 layers, as is required for Type 4A. This is a section of a Type 4C wall. It shows that the walls, floors, and ceilings may be exposed, but only to the extent stated in section 602.4.2.2.2, and they still must provide 2 hours of fire resistance. To wrap up, we would like to provide some resources for you to assist you with your understanding of mass timber in the International Building Code. Here are the code sections that are applicable to the tall mass timber provisions in the IBC. For a more in-depth review of the code sections listed here, please see the IBC code commentary. There's a ton of free information on the TWBAH website, and we are always updating our various standards. The latest and greatest content can be found online. That's the end of our presentation today. Hopefully, this has generated some questions from our audience.